Jai Hind everyone. Once again, I welcome you all in my channel, Physics with Rumeet. In this video, we will study about refraction at spherical surface. That is, we will study about what are spherical surfaces, what are various types of spherical surfaces, and how refraction takes place in a spherical surface. Okay, that means we will derive the relation between the object distance, image distance, and the refractive index of the medium through which the light is passing, as well as the refractive index of the spherical refracting surface. So, without wasting any time, let's begin. Now, the first of all, we should know what exactly we mean by spherical refracting surface. So spherical refracting surfaces are what? It is basically it's a portion of a refractive medium whose curved surface forms the part of a sphere. Okay, let's understand this with the help of a figure. Now over here, this XII surface which you are seeing, this is a spherical refracting surface. This is a denser medium, say whose refractive index is mu. This denser medium could be anything. This could be glass, it could be any transparent medium. And this is kept in some rarer medium. Okay. Now this curved surface which you are seeing, this curved surface is the spherical refracting surface, and we call this refracting or such type of a refracting surface as convex refracting surface, because as you can see this bulge part is outside. Okay, so such type of surfaces are known as convex refracting surface. Now this curved surface basically is a part of a sphere, or you can say it's a part of some spherical body whose center lies over here. Now this point C, that is the center of this spherical surface, is known as the center of curvature. This is exactly the same terminology we are using it over here, which we use it for spherical mirrors. Okay. Now let's look at the other refracting surface. Now over here, if you see this bulge part is lying inside. That is, it is towards the, this bulge part is towards the denser medium, or towards the, you can say the, or inside this denser medium. Okay. Now again over here, this XPY surface which is there, this is the spherical refracting surface, and we call this refracting surface as concave refracting surface. Now here C, which is the center of curvature, is lying outside the denser medium. Okay. Now let's move to the refraction at convex spherical surface. In this case, we will do where the object will lie in a rarer medium and the image formed is real. Okay. So basically here, now we will derive the relation between UVR, that is the radius of curvature, and the refractive index of the medium. Now let's begin. Say this is a convex spherical surface. This line which you are seeing, this is the principal axis. The rarer medium has the refractive index of mu1, and the denser medium, of which this refracting surface is made up of, has a refractive index of mu2. This point P, where the spherical refracting surface and the principal axis is meeting, this point is known as pole. Now say over here, an object O is lying. Now object O is a point object which is lying outside this denser medium. That means it is lying in the rarer medium. Okay. And over here we have center of curvature, that is C. Now before we start with the derivation, there are certain assumptions which we should know or which we should consider while we derive the relation between UVR and mu1, mu2. Now the assumptions are that the aperture of the refracting surface is small. That is, this aperture, that is the size of this refracting surface, we consider it as very small. Second assumption we consider over here is that the object is a point object which is situated on the principal axis. And third, the incident and the refracted rays makes a small angle with the principal axis. Means the angle which the incident angle or the angle of refraction which we will obtain over here will be very small. Okay, now since this aperture of the refracting surface is small, so obviously those angles would also be small. So basically the figure which you are seeing over here, it is basically, you can say, it is an extended form of the real figure. Okay, in one way, what we have done is we have compressed figure laterally, and we have elongated the figure. Okay, so now let's begin. Now the instant ray from object O, say it strikes the refracting surface over here, say at point A. Now from point C, if I join A, then this dotted line basically represents the normal. Okay. Now this angle will be your angle of incidence, which we represent by I. Now, since the ray is traveling from rarer towards denser medium, so over here at A point, the refraction will take place and the light will bend towards the normal as it is traveling from rarer to denser. Now, the angle which the refracted ray, say, makes with the principal axis, we call that as angle beta. And the point where this refracted ray meets the principal axis, at this point, we obtain the image I. Because the second ray we can consider, say it goes straight along the principal axis and it meets at point I, because any ray which is passing through the pole will not undergo any deviation. Reason being, the angle of incidence for any ray which is passing through pole would be zero. So angle of refraction would also be zero. Okay. Now this angle will obviously be angle of refraction, and this angle, that is that normal which is making with the principal axis, we call this angle as gamma. Now if I drop a perpendicular from A onto the principal axis, it meets at point N. Okay. Now, since aperture of this spherical surface is very small, so for all practical reasons, we consider that P and N are lying very, very close to each other. We don't consider P and N as two separate points. We consider P and N as a same point. So for all practical reasons or for all mathematical calculations, we will consider that the P and N to be the same point. Okay. Now the angle which the incident ray is making with the principal axis, we call this angle as alpha. I hope this diagram is clear to all of you. I once again repeat it. From O, which is the point object, the incident ray begins. It strikes the refracting surface, spherical refracting surface at point A. Now over A, at point A, the refraction takes place and the light ray bends towards the normal and it strikes the principal axis at point I. Now at this point, the point where the principal axis and this refracted ray meets, that is the point I, at this position we get the image of this object O. Now the angle which incident ray makes with the principal axis, we call that angle as alpha. Angle which the refracted ray makes with the principal axis, we call that angle as beta. And the angle which normal makes with the principal axis, we call that angle as gamma. Now AN is the perpendicular to the principal axis and P and N are 2 points which are very, very close to each other. Okay. Now this distance, that is the distance of object O from the pole, obviously will be U, that is the object distance. This distance, the object of the distance of the C from the pole, we call that as the radius of curvature, that is this PC is the radius of curvature, and the distance of image from pole, we call this distance as V. U and V and R, U, V and R are the standard nomenclatures which we use it for object distance, image distance, and for radius of curvature. Okay. Now let's begin with the mathematical part. Now over here, as we have already discussed, angle AOP is alpha, angle AIP is beta, and angle ACP is gamma. Okay. Now, Consider triangle AOC. Okay. Now, if you look at this triangle AOC, here, if you see I is the exterior angle and alpha and gamma are interior opposite angles. So if I use the property that the exterior angles equals to the sum of opposite interior angles, I can write I in terms of alpha and gamma as I equals to alpha plus gamma. Over here, since the aperture of spherical surface is small, now this is spherical surface, its aperture is small, so I can write alpha as tan alpha and gamma as tan gamma. In fact, beta can also be written as tan beta. Okay, because since the aperture is small, so all these angles alpha, beta, and gamma would also be a small angle. So the same expression I equals to alpha plus gamma can be written as I equals to tan alpha plus tan gamma. Okay, let's call this as equation number 1. Now from right angle triangles ANO and ANC, okay, I can write tan alpha as AN upon NO and tan gamma as AN upon MC. Okay, now when I substitute the values of tan alpha and tan gamma in this equation, equation number 1, I get I equals to AN upon NO plus AN upon NC. Okay, and we call this say as equation number 3. Now, since the aperture of the refracting surface is small and point P lies very, very close to point N, that is P and N as we had discussed earlier, are very, very close to each other. Therefore, I can write NO as PO and NC as PC. That is, this distance NO would almost be equal to PO, and this distance NC will be almost equal to PC. So from equation 3, what I do is I replace NO with PO and NC with PC. So when I replace NO with PO and NC with PC, equation 3 becomes I equals to AN plus PO plus AN plus PC. And say this is equation number 4. Okay. Now, similarly, if you look at the triangle ACI, now in the ACI triangle, if you see, gamma would be an exterior angle and R and beta would be two interior opposite angles. So from triangle ACI, I can write gamma equals to R plus beta or R equals to gamma minus beta. Similarly, I can write gamma minus beta as tan gamma minus tan beta since beta and gamma are small angles. And again, over here, if you see the triangles ANC and ANI, I can write tan gamma as AN upon NC and tan beta as AN upon NI. Okay, and again, since P and N are very, very close, so NC will be replaced by PC and NI will be replaced by PI. So finally, what we get over here as tan gamma as AN upon PC and tan beta as AN upon PI. Now, when I substitute the values of tan gamma and tan beta from this relation into equation number 5, I get R equals to AN upon PC minus AN upon PI and say this is equation number 6. Okay. So from, if you see, from equation 4 and equation 6, what we have done is we have written I and R in terms of PC, PI, and PO, and obviously AN. AN is the term which is common in all the relations. Now, let's apply the Snell's law. Now, when I apply Snell's law, I can write the relative refractive index of the denser medium with respect to rarer, that is mu2 upon mu1 equals to sin I upon sin R. Okay, or when I do the cross multiplication, this becomes mu2 sin R equals to mu1 sin I. I have simply done the cross multiplication. Now again, since I and R are small angles, so sin I will become I and sin R will become R. Remember that whenever we have a small angles means the angles which are less than 5 degree or 6 degrees. These are the small angles, and for small angles, if I take a trigonometric relation, like say if I write the sine of that small angle or the tan of that small angle, then the value of the sine and the tan function would be equal to the value of that angle itself, provided that angle should be written in radians, not in degrees. Okay. So over here, since I and r are small angles, so what I'm doing is I'm writing sine I as I and sine r as r. Okay. Now let's move further. Now, if you see over here from equation 4, we have written the relation of I in terms of I was what? I was an upon no plus an upon nc, or an upon po upon an upon pc. Okay. And in equation number 6, if you remember, we have written the r in terms of gamma and beta. Okay, that is r was what? R was tan gamma minus tan beta, and tan gamma was what? An upon pc, and tan beta was an upon pi. So what we do is we combine those 4, 6, and this equation 7. And what we obtain over here is that instead of I am writing En upon Po plus En upon Pc. And instead of R, I am writing En upon Pc minus En upon Pi. Okay. Now, if you see over here, An is common. So all the An's cancel. And when I multiply mu1 inside the bracket, I get this relation. That is mu1 upon Po plus mu1 upon Pc equals to mu2 upon Pc minus mu2 upon Pi. Okay. Now on rearranging, that is, I am taking all the Pc terms onto the right hand side of the equation. That is, here I have mu2 upon Pc. I am taking this mu1 upon Pc also onto the right hand side. And this mu2 upon Pi, I am taking it on the left hand side. So what I have done is I have collected all the Pc terms together and the Po and the Pi terms together. So what I obtain over here is a relation which says mu1 upon Po plus mu2 upon Pi equals to mu2 minus mu1 upon Pc. Okay. Now, what I will do next is I will substitute u, v, and r in this equation. But when I substitute u, v, and r, I'll substitute it along with the sign convention. Now see, PO will be what? PO will be U. Okay. And what will be the sign for U? It should be negative. Why? Because if you see, the incident ray is traveling in this direction. That is traveling from left to right. Okay. And if I have to measure U, I have to move from P towards O. That is, I have to move against the direction of the incident light. So here U will be what? Negative. Now, if I have to measure V, how I have to move? I have to move from P towards I. That means I have to move like this, in this direction. That means I have to move in the direction of the incident light. That is from left towards right. So V will be positive. Similarly, for measuring R, I have to move from left towards right. So R will also be what? R will also be positive. Okay. So that's why we have used this sign convention. That is PO as minus U, PI as plus V, and PC as plus R. Okay, now when I substitute these values in this expression, what I get over here is mu1 upon minus U plus mu2 upon plus V equals to mu2 minus mu1 upon R. Okay, and when I rearrange this, I get a relation mu2 by V minus mu1 upon U equals to mu2 minus mu1 upon R. Okay. Now, in the next one, the second case which we will do over here, we will do again the refraction at convex spherical surface. Now over here, the object lies in a rarer medium, but the image which will be formed now will be a virtual image. The previous one, what we did over there was that the object was lying in the rarer medium and the image which was formed was real. Now the image which will be formed, that will be virtual. Okay. Now, the assumptions again are same, which we have taken it earlier. That is, the aperture of the refracting surface is a small object, is a point object, which is situated on the principal axis. The incident and the refracted rays make small angles with the principal axis. Okay. Now, basically, if you see um, the different types of cases for the refraction at spherical surface, whether it is convex or concave, there will be some 9-10 cases which will arise. Okay, basically, and the basic difference in all these cases are just in the ray diagram. If you actually go through the mathematical part, that is the derivation part, you will find the similarity, means the derivations are almost similar for all the cases. The major difference which you will see over here is only in the ray diagram. You have to basically focus on making the correct ray diagram. If you have made a correct ray diagram, that means half of your problem has already been solved. Okay, that you'll see as we proceed further. You'll see that what is the major difference between these different types of cases. Okay, so let's begin. Now, this is the convex spherical surface. Outside, that is, this rarer medium is mu1, denser medium is mu2. This is the principal axis. This point is P, that is the pole. This dot which you are seeing over here is C, that is the center of curvature. And here, this is the object O. Now, the difference between this diagram and the previous diagram is, you see that this object O is lying a bit closer to the pole of the mirror. That is, it is lying a little bit nearer to the spherical surface. Okay. Now, let's begin. We have an incident ray which starts from O and it strikes this spherical surface at this point, which is point A. Now again, when I join C with A, I get this dotted line, and this dotted line will act as a normal to this spherical surface. Now this angle will be angle of incidence I. Now again over here, since the light is traveling from rarer to denser, the incident ray will obviously bend towards the normal. Okay, but since this O is lying very, very close, you see that this angle of refraction, obviously this refracted ray is bending bending towards the normal, but it will not bend that much that it will touch the principal axis. That means you'll see that this ray will be going away from the principal axis, right? Now this angle will be angle of refraction, that is R. Okay. Now, in order to get the image, we need two rays. So, second ray, we take it as the ray which is going along the principal axis like this. And as we can see that both these refracted rays are diverging, that it is going away from each other. So, obviously, these two rays are never going to meet. So, what we do is we extend this ray backward, or both the rays basically, we extend it backward. And we see that when we extend both these rays backward, they appear to meet at this point. So this point basically will act as the virtual image, or basically we can say that for this object O, the virtual image is getting formed at this point. Okay, I hope this is clear to everyone. Now, this angle, that is the angle which incident ray makes with the principal axis, we call this as alpha. This angle which the refracted ray makes with the principal axis, we call that as beta. And this angle which the normal makes with the principal axis, we call that as gamma. Okay. Now it's very easy to remember that the angle which is formed at O will be alpha, angle which is formed at I will be beta, and the angle which is formed at C, that would be gamma. Okay. Now from A, I drop a perpendicular onto the principal axis, and this perpendicular meets at point N. Okay, again, this P and N point will be lying very, very close to each other. Okay, now this basically completes your ray diagram. And if you mark the distances, obviously this distance will be U, that is, this is the object distance from the pole of the mirror, pole of the spherical surface. This distance would be V, that is, this is the image distance from the pole, and this distance would be R, that is the radius of curvature. PC would be R. Okay, now let's begin with the mathematical part. Again, as we have discussed, angle AOP is alpha, that is, this angle is alpha. AIP is beta, that is, this angle AIP, this is beta, and angle ACP is gamma. Okay. Now from triangle AOC, if you look at this triangle, for this triangle, the exterior angle is I, and the interior opposite angles are alpha and gamma. So I can write the relation I equals to alpha plus gamma. Okay. Now again, since alpha, beta, and gamma are small angles, so I can write alpha as tan alpha, beta as tan beta, gamma as tan gamma. So this relation becomes I equals to tan alpha plus tan gamma. Okay. Now again, if you consider the triangle ANO and triangle ANC, I can write tan alpha as what? Tan alpha as AN upon NO and tan gamma as AN upon NC. Okay. Same thing. If you see, if you just consider steps, these steps are exactly the same. The steps which you have done in the previous case, they are exactly the same. Now again, from equations 1 and 2, I can write I equals to AN upon NO plus AN upon NC, right? Now again, this P and N are very, very close. So NC and PC would be same. Similarly, NO and PO will also be same. So since the aperture of the refracting surface is small and point P lies very close to point N, I can write NO as PO and NC as PC. Therefore, this equation becomes I equals to AN upon PO plus AN upon PC. What we have done, we have simply replaced NO with PO and NC with PC. So this becomes your equation number 4, which gives you the relation of I in terms of PO, PC, and AN. Okay. Now, similarly, from triangle ACI. Now, if you look at this triangle ACI, okay. Now, from triangle ACI, what could be the which one would be the exterior angle? Now, if you look carefully, the exterior angle for this triangle would be this angle. This angle, and this angle is basically is nothing but it is angle R, that is this angle, because R, this and this angles are vertically opposite angles. Okay, so for triangle ACI, okay, the exterior angle would be what? Exterior angle would be R, and interior opposite angles would be gamma and beta. Okay. Now, R would be can be written as tan gamma and tan beta, because gamma and beta are small angles, so I can replace gamma with tan gamma and beta with tan beta. This is equation number 5. And from triangles ANC and triangle ANI, I can write tan gamma as AN upon PC and tan beta as AN upon PI. Exactly the same steps which we have done in the previous case. Okay, so when I replace tan gamma and tan beta with AN upon PC and AN upon PI in equation number 5, the equation number 5 becomes R equals to AN plus PC plus AN upon PI, which we term it as equation number 5. Okay, now again when we apply the Snell's law. Now when I apply Snell's law, this becomes mu, that is the refractive index of denser medium with respect to rarer, that is mu2 upon mu1. This is equals to sin I upon sin R, or mu1 sin I equals to mu2 sin R. Or the same thing can be written as mu1 I equals to mu2 R, because I and R again are small angles. Okay. Now this becomes equation number 7. Now what we do is we just combine equation number 4, 6, and 7 together. So when I combine equation 4, 6, and 7, equation 4, remember, this gives you a relation of I in terms of AN, PO and PC. And equation number 6 gives you the relation of R in terms of AN, PI and PC. Okay, so when I club those two equations with equation number 7, I get mu1 into AN upon PO plus AN upon PC equals to mu2 AN upon PC plus AN upon PI. Okay, now all the ANs cancel, as you see that the AN are common, so I can cancel all the ANs. When all the ANs cancel and when I multiply mu1 and mu2 inside the bracket, what I get over here as mu1 upon PO plus mu1 upon PC equals to mu2 upon PC plus mu2 upon PI. Now the next step what I do is I take all the PC terms on one side of the equal to sign and I keep PO and PI terms on the other side of the equal to sign. So when I take this mu1 upon PC onto the other side, this expression becomes mu1 upon PO minus mu2 upon PI equals to mu2 minus mu1 upon PC. Okay. Now, in the last step, what we do is we replace PO, PI, and PC with U, V, and R respectively. Now, in this figure, if you see, what should be the sign convention for U? This is the direction of incident ray. For U, I have to travel opposite to the direction. So U is negative. For V, again, I have to travel opposite to the direction of incident ray. So again, V over here is negative. In order to measure R, I have to travel in the same direction as that of an incident ray. So R over here is positive. So when I substitute the values of U, V, and R along with the sign convention in this expression becomes mu1 upon minus U minus mu2 upon minus P equals to mu2 minus mu1 upon plus R. Or this expression becomes mu2 upon V minus mu1 upon U equals to mu2 minus mu1 upon R. Now, if you see the final result, that is this one, you see that the final result for the virtual image as well as for the real image is exactly the same. Okay, so this relation does not get affected whether the image which is formed is a real image or the image which is getting formed as a virtual image. I hope this derivation and this figure is clear to all of you. Okay, now in the next video, we will study about the refraction at concave spherical surface. So stay tuned and please take care of yourself. Goodbye.